Hi friends, welcome to the technical overview of the UAP detector. I'll just quickly tell you that, so these are some detections that we made, but this right here is the reason why I got started. I would see frequently when I loaded up objects like this that would appear and disappear over the course of a couple seconds, and maybe it sounds silly, but I was speculating on the fact that a four-dimensional object passing through a 3D space would appear as a sphere, and that appeared to be what we were seeing just crop up and disappear next to the ISS from time to time. It turned out really quickly in my building this out that what we were in fact looking at was a kind of a secondary lens flare. Whenever we were seeing these objects, there was a very bright spot somewhere on the ISS, and so it was causing a reflection off the camera, which was making these objects appear. And so that's what got me started on this whole project in the first place. But I realized soon that it was really, really difficult for human beings to do this work, and there should be something monitoring what's going on up here. It's a shame that we don't have access to the actual high-def feed. High-def points down at the Earth, but we're just working with what we have. I'll give you a quick overview of how it works. The main body of the program is inside process frame here, where we start up, and as you can imagine, the real challenge of the project is we're receiving 60 frames a second from YouTube, and to keep everything going and working perfectly and smoothly and properly, we have to make sure that all processing is done in under 18 milliseconds per frame. And so that means we've got to run the recurrent neural network. We have to do the first principles processing. We have to resize it all and adjust it for display. And we have to hand it to the streaming all within 18 milliseconds. And so that was really the hardest part of the project in a lot of ways, aside from just the pure mechanics of it. But to ensure that we're keeping under 18 milliseconds took a lot of tinkering. We're there now, and that's fantastic, and I'm quite proud of that and happy with that. So really, the feed comes in. There's big black borders on it. We have to trim those off and start running our detections on it. And so detections essentially has this threaded recurrent neural network, which every 2 seconds it processes a frame and gathers what sections are definitely not going to be anything and where we can start searching in these space windows. So that saves us a lot of time running that every 2 seconds. And then we break down into detect anomalies, where it's essentially looking against the black background of space for objects that have a certain level of brightness, a certain contour, meet all the criteria that will allow it to be detected. But then, of course, another layer of filtering, because there's frequently lens flares. There's the moon. There's objects that we don't want to be capturing, and so again, that uses the feedback from the recurrent neural network that helps us avoid frequent mistakes. It does make some, but that's totally fine. It'll be 100 captures in a day, and maybe 75% of them are something that we want, and 25% are uninteresting. So, and I'll explain in my next video exactly what's prosaic. Almost everything's prosaic. I've included this background because it's intriguing, but I'm quite sure that this is, well, not quite sure, but I suspect that these are cosmic rays hitting the lens. You might be inclined to think that that's a meteor, but we're a few hundred kilometers above the atmosphere there, so I don't think it's that. you know, we are processing in full color, which was a challenge as well. And just, you know, that's how it breaks it down. I'll share with you how, you know, we've got this kind of constant handling. There's a lot of things that will be, this is so I can tinker and add different things and change things, but I quickly realized that this was a little too difficult, so I built out this console, which allows me in real time to make changes. We've got a darkness event happening right now, but I've got this real-time parameter control here so that I can edit. And it's quite tricky because we have so many different camera angles. It's hard to be perfect all the time, but the camera angles tend to shift on a day-to-day basis, like 24 hours and maybe 5 days at a time. So we can, with some manual change, we get to be pretty efficient. There's logging. The logging is what was necessary to understand what was taking so much time. The stream is really cool and took me a little bit to get ready, and so essentially I'm using this kind of single file, single operation, what's it called, MNMN type, MNNM architecture, or kind of a stop architecture. Single use architecture is what I'm trying to use here, and it works quite well. So, you know, that's just the general overview. You're very welcome to download the code and run this on your own. And the RCNN is attached in the files out here, so you can see if you really want to run this at home. But we've built the streaming, and when I say we, I do mean me and Claude, essentially. Thanks so much, and I'll get through and show you what's prosaic in just a moment. All right, thanks for joining me for just a technical look at how it works.